We are now going to apply the concepts and the implications of external diffusion processes on first order reactions. So it's important that you switch your minds to first order reactions. In the rate equation, we must now remember that the concentration we are interested in is the surface concentration. We now know that we have an extra equation that we can use to calculate that surface concentration, in that at steady state, the rate of reaction at the surface and the rate at which the reactant is delivered to that surface must be the same. Just a reminder on why we need this conversion factor is, if you go to the slides where we first encountered Kc, must remember that that gives us a flux, which is moles per second per external catalyst surface area. So we need this conversion factor. Please revise if you are still lost regarding these conversion factors. Now, since we have a first order rate equation, it is possible to get an explicit equation where we make surface concentration the subject of this relationship, and then we can do some algebra to prove that we can write the surface concentration as a function of the bulk concentration, which is fantastic because the bulk concentration is the one that we can measure. In our rate equation, we can now substitute this whole equation or the expression that we derived for the surface concentration, and this gives us a rate equation that has got lots of constants. So it's our rate constant Ki multiplied by the surface concentration, which results in an expression that has got lots of rate constants multiplied by the bulk equation. So we can then combine all our rate constants into one variable that we call the effective rate constant. So that's the rate constant that results as an effect of both processes in series, the rate of the mass transfer and the rate of the surface concentration. So it is convenient for first order reactions to write that rate constant rather as a resistance. So we are going to use the analogy with electrical currents, where we have the rate of the current or the stream is equal to the driving force or the volts divided by a resistance. So make sure that you can see that the resistance in our case is 1 divided by my rate constant. That gives me the resistance to the rate. Right, so now, just like in currents, if we have a first order reaction, the driving force or the volts is first order in concentration regardless of whether we consider external diffusion or the intrinsic reaction rate. For other order reactions, we cannot do that because our driving force for the reaction is not the same as for our mass transfer rate. So since we have processes that occurs in series, first we have the external process followed by a series process, the reaction rate, we can sum our resistances in series. So it's worthwhile to see if you take this external or the effective rate constant and you take its inverse, make sure that if you write it in terms of resistances, you are able to prove that the overall resistance to my rate is the sum of the two resistances, and algebraically that you can also derive this equation. So let's explore this resistance-based analogy for our rate steps. So if I have an increase in the rate of external diffusion, so my rate constant there increases, I have nice high shear, I have very small particles, it means that the resistance to external diffusion will go down. So what is the implication? We know that we have a surface concentration that will fall within these ranges. It will always be less than or equal to the bulk phase concentration, and it cannot go less than 0, of course. So if I look at my rate of diffusion, as this term goes up, If the rate stays the same, it must imply that the difference between the bulk and the surface concentration becomes smaller and smaller. So we are now going to discuss the limiting case where that difference becomes so small that it's really negligible, and we can say that my surface concentration is pretty much equal to the bulk concentration. What does that imply? It means the resistance to the reaction rate is much bigger than the resistance to the external diffusion process. In other words, Ki is small relative to Kcam, which is really large. In this limiting case, we say that the reaction rate step controls the rate. We can completely neglect the effect of external diffusion processes, and if I look at my resistances, this one pretty much becomes equal to 0 because I have, let's say, 1 divided by 1,000,000. This is 1 divided by 0.01, and my effective rate constant becomes equal to my normal rate constant of the reaction, and surface concentration and bulk concentration becomes the same. Sorry, there's a dot missing there. And I can proceed as if I would normally have before we started introducing the concept of external diffusion. So let's now consider what happens in the other limiting case where my Kcam is really small. So the rate of external diffusion is very slow. That implies that the resistance to external diffusion becomes big compared to the resistance of the reaction rate. So the implication on my surface concentration, once again, if I consider my rate of the diffusional process, this becomes really small. So the difference between the bulk concentration and the surface concentration goes up to the limiting case where Ca surface actually becomes equal to 0. So in the restaurant, don't you miss the days when we could order chips in a restaurant? So in the restaurant, that surface concentration, that chip in your plate, as soon as it hits the plate, it disappears. So actually what you will end up with is an empty plate or a 0 surface concentration, because the rate of delivery is much smaller than the rate at which you can eat your chips. Implication for the resistances, the resistance to external mass transfer controls the rate. Big resistance, it controls the rate. So the word we use for rate controlling, that's the same as saying external mass transfer controls the rate, surface concentration is equal to 0. The effective rate constant in fact becomes equal to Kcam because this term relatively goes to 0. This is 1 divided by 1,000,000. This is 1 divided by 0.01. Whether I include this or exclude it, it's not going to make a difference to my effective rate constant. So in my rate equation, in my mole balance, I will only consider the rate of external diffusion in the limiting case where Ca surface is equal to 0, and I end up with this first order rate equation where Kcam is my rate constant, Ca bulk is my driving force. This, of course, also happens for other order reactions, even though I can't write it in terms of resistances, but the implication is still that when external mass transfer controls the rate, the surface concentration will go to 0, and I will have a rate that appears to be first order. What the implication is that you will never discover whether the rate at which I can eat chips will depend on whether my chips plate contains 1,000 chips or 10 chips, because I will always have an empty plate. I will never be able to see what the effect of the concentration is on my rate, because I will always measure a first order rate if external mass transfer controls the rate. So for the reactions where we don't have first order rate expressions, it is important to remember that the concept of an effective rate constant and the sum of resistances does not apply. It's a frequently made mistake by students and one that will result in immediate failure if you want to apply that concept to reactions that is not first order. Here, like in that 4.2 for instance, you must resort to calculating the surface concentration by applying this algebraic equation. Rate of the reaction is equal to the rate of diffusion. Note that in this equation, for instance, just to mix it up, I've expressed the rate on a volumetric basis once again. Of course, when you are told that the rate is controlled by external mass transfer, that is a synonym for the fact that CA surface must then be equal to 0. So then you are in fact told in another way that the surface concentration is equal to 0. So please don't make that mistake. Apply first order principles to multiple order or non-first order reactions. So remember that the surface concentration, once again, you can get multiple solutions if you apply that equation to solve for the surface concentration. If you want to use that in Fsolve or on your calculators, give it a first guess that is in the applicable range. So surface concentration must be more than 0 but less than the bulk phase concentration. For rate equations, where the rate is actually a function of more than one reactant, your job will be to determine the diffusivity of each of those reactants separately in the mixture, and the one that's got the lowest diffusivity will have a surface concentration that is less than the bulk concentration. So if component A diffuses slower than component B will have time to reach that surface, and it will actually be at the bulk concentration at the surface. In your rate equation, you only need to calculate the surface concentration of A. So you will only apply the diffusivity of A, the external mass transfer of A. And of course, the opposite is true. If A diffuses faster than B, it will be present at its bulk concentration rate. So the resistance to external mass transfer for component B will dominate. So you will have bulk concentration of A, but the surface concentration of component B. You need to understand this for your design project next semester, but this will not be tested in CRO test, TATS or exams.